Okay, so let's get started. First, thank you for everyone to coming, and thank you for Alejo to start to do this seminar. Alejo is a computer vision engineer in Zurich, in Facebook in Zurich, and he has done the PhD under the supervision of Javier Cieira here in University of Zaragoza. The presentation he's going to do today is going to be about SLAM for virtual reality devices and augmented reality devices. So if you want, the floor is yours.
Yeah, thank you very much, Pablo, for the introduction and also for the invite to you and Javier and Anna. It is a pleasure to be here. And as you said, I'm going to talk about SLAM for AR and VR devices. So I'm going to talk about some of the work that we do at Facebook for VR and also AR. So I will give you a brief intro about myself. I studied at the University of Zaragoza, as you said. I did industrial engineering and the master in robotics. And then I did a PhD in computer vision under the supervision of Javier Cieira. As a part of my PhD, I did 2 internships, one at Google and another one at the University of Pennsylvania. And after the PhD, I joined Meta as a computer vision engineer to develop tracking technologies for VR and AR. So this is going to be a talk about SLAM, and I will give you a brief intro into SLAM. But probably all of you or most of you already know about it, but SLAM is the problem of localizing a device, in this case a robot, using input sensors. For example, a camera is the most common input sensor that is used for solving the problem of SLAM. And a camera, what it does is to just observe the world, try to match some landmarks like the green landmarks that you see here, and use those landmarks to estimate the relative position from frame to frame. As the robot moves, the uncertainty of the device or of the robot increases until we are able to observe the same features again, like for example in this case the house, close the loop and reduce the uncertainty of the robot. So SLAM is the problem of simultaneously building a map of the environment, in this case the green landmarks, and also estimating the position of a device that is moving. SLAM is quite recent. The first formulations were developed around 20 years ago or even more. And around 15 years ago, we had the first demonstration of real-time SLAM on a mobile phone, while the last 2 years have been mainly used to productize the SLAM into vacuum cleaners and other products like VR devices like Quest, or AR, like ARKit from Apple or ARCore from Google. SLAM can use different sensors. The camera is the most common one because it's very cheap and accurate. And when you use only a camera, we are doing Visual-Inertial Slam. If you combine a camera with also an inertial sensor like gyroscopes or accelerometers, then you do Visual-Inertial Slam. IME sensors are pretty good because they have a very high frequency, like 1000 Hertz. The problem of them is that they are not as accurate as cameras, so if you combine them together, you can get the best out of the 2 worlds and get a very robust and accurate system. In our devices, we use several cameras and an IME sensor for tracking. Additionally, you can also combine this with depth sensors to estimate a way more accurate map of the environment. This is a demonstration of a Visual Slam from a colleague from my office. The main advantage of this SLAM system is that it's super fast, so that enables very, very fast motions and aggressive motions, as you saw in that first part of the video. And this system is only using vision. As you can see, it's reconstructing the environment. You can see the green points and also the trajectory of the estimation of the camera. So many SLAM systems have these building blocks, or at least some of them, and I will briefly talk about them. The first one is initialization. Then we have map building, then pose and map optimization, or band aliasment, and finally keyframing to reduce the size of the map. For initialization, I'm not talking much because I will talk way more later, but basically it's the problem of initializing the relative pose between frame 1 and frame 2 so that you can bootstrap your system. Once you have the relative pose between frame 2 and frame 1 estimated, you can start to build your map. For that, you need to extract features. Features are extracted normally in parts of the image that are very distinctive. So, for example, the nose of the duck, as you can see, is pretty easy to tell where it is in the left image and also in the right image. So it's kind of easy to detect this nose, and also once the nose is detected, which is this patch here, and this set of numbers, we can actually try to find this this patch in the second frame. For that, we can use the epipolar line, and search along the epipolar line until we have a perfect match, just in the nose in the second frame, and then we can triangulate and get a 3D point. So we can repeat that for many points, and the problem of this initialization is that the point is not going to be very accurate, and if we project it back into the frames, we are going to see that the representation error is high. And apart from that, as I told you, we also have the relative pose coming from the IMU. So we have the relative pose coming from frames, from the camera estimation, and also from the IMU. And ideally, we would like to fuse them together so that we can estimate the parameters of the IMU and get predictions later on. So we can fuse the camera and IMU sensors in a global optimization, a nonlinear global optimization that is called Visual-Inertial Slam adjustment, where we optimize both the IMU integration error and the representation error to estimate the position of the cameras and also the parameters of the IMU, like for example the bias of the gyroscope and the accelerometer. Apart from that, we also build a map of. We can also build a map of the environment. For that, we use the concept of keyframes because for most of the frames, we have a lot of overlapping features and they are kind of redundant. So when we are tracking a frame using some features, at some point we realize that with those features we cannot track it anymore. So we have to introduce new points, and at that point we can introduce a new keyframe. And basically, our map is composed of keyframes that are, let's say, essential because they are the minimum set of frames that can be used to describe the scene. And we also have the points. So once we have this point cloud and the keyframes, we can run a global band adjustment and optimize the points and the position of the keyframes. This is an example of a SLAM system I work on during my PhD. This is only using vision, and the main novelty of our approach back then was that we combine features, points, high gradient points, which are the red ones in this image, with planar constraints or with superpixels, which are. So we use superpixels, which are the blue points that you see here in the image. And we assume that those superpixels are planar, and we basically do the same. We try to initialize them and optimize them by triangulation and also by minimizing representation error. In this case, representation error of the superpixels is based on the contour of the superpixel, so we minimize the representation error of the contour between multiple views. And by doing that, we can estimate a tensor map of the scene. This is another example from my PhD. This was part of my internship at Google, and here I work on something similar, but in this case I didn't use planar constraints. I only did point-wise reconstruction, and the main challenge here was that we had to do this for very big data sets. So we had to do it on the cloud, like parallelizing all the work. And this is an example of a small neighborhood, a few streets in the city of Zurich. So now I'm going to talk about SLAM for VR devices. Quest 2 is the product that we shipped a couple of years ago. It has is a standalone, so it doesn't have any output cameras. Everything is processed in the device. So we have 4 cameras and one IMU to estimate the position of the headset. And we have LEDs in the controllers to also estimate the position of the controllers with respect to the headset. The controllers also have an IMU, and basically, in both cases, both in the controllers and in the headset, we use similar tracking and optimization technologies. This is an example of a VR game. This is called Table Tennis 11. And this is the one I like the most because it's super realistic and it actually feels like you're playing ping pong. And this is me playing with a colleague from my office, with Alberto. Each one of us is playing in his apartment. And at the same time that we play, we see each other, or at least this avatar version of us. And we can talk to each other and play and have fun. This is the game that I like the most. So this is a brief summary of our SLAM system, the one that we use in Oculus Quest. Here we have 3 threads, an IMU thread, a tracker thread, and a mapper thread. In the IMU thread, we receive data from the gyroscope and the accelerometer, and we can basically integrate this data and get the position of the device in real time and very fast, like at 1000 Hertz. The problem is that the IMU is not super accurate, and we need to fuse this data with camera data that runs at 30 frames per second, and we do that in the second thread, in the tracking thread. So here we receive the images from the 4 cameras, and first we do image processing. We build the image pyramids so that we can compute or track features at different scales. Then we do a feature selection step where we get the features from the map and we project them into the current frames, and basically we try to match them. If we find them, we do subpixel alignment, and we send this data, the measurements, together with the IMU data, to a Visual-Inertial Slam window post-estimation. So in this post-estimation, we have a small sliding window of a few frames, and we do post-estimation. Once the pose is optimized, we decide if the current frame is going to be a keyframe or not. If it is going to be a keyframe, then we send it to the keyframe queue, so that in a third thread is added to the current map, and we can optimize the current map. Basically, we do again Mandela adjustment, and we optimize the parameters of the map, the points and the keyframes. Yeah, I forgot to mention that in the IMU thread, we also have a feed-off attitude filter that is mainly used to initialize or at least to initialize the rotation of the camera for initialization and also for relocalization. For relocalization, it's actually used to do the DMU weight. Also, in the mapping thread, we have the relocalization training, where we use the keyframes to train a bag of words and then use it for relocalization when the system is lost. Finally, in the Visual-Inertial Slam window post-estimation, we also do line calibration. This is very important because some of the parameters can change, like for example, the focal length of the cameras with temperature, and it is important to always calibrate intrinsics and extrinsics of the camera and the IMU. Some parts of this system, like especially the image processing parts, like image pyramids, computation, patch matching, and subpixel refinement, can be accelerated in the DSP, and also feature extraction. So we have a module called point sheets that basically is estimating. Basically, what this module does is to first extract features if we have a new keyframe, and then it triangulates those features by doing back-epipolar matching. So we have a set of frames, past frames, that we use to back-propagate the features, and we do triangulation. using similar techniques to the one I explained before. And this is a video.
Oculus Insight is our revolutionary VR system that uses computer vision algorithms to enable real-time room mapping and positional tracking on the Oculus Quest and Rift S headsets. Oculus Insight uses an approach called Visual-Inertial Slam to track the position of your head and constellation tracking to track your hands. Together, these technologies precisely translate your movements into VR, so you feel truly present in the virtual experience. Oculus Insight relies on 3 types of sensor data. Image data from cameras in the headset to generate a 3D map of the room, pinpointing landmarks, such as corners of furniture and patterns on your floor. Rotational velocity and linear acceleration data from the inertial measurement units in the headset and controllers track your head and hand movements. And infrared LEDs in the controllers are detected by the headset cameras, further improving Insight's ability to track the position of the controllers. As you move through your space, Insight detects unique image features in the room and triangulates those points in 3D, using up to 30 views per second. Oculus Insight uses a breakthrough approach for multi-sensor nonlinear optimization to fuse all of this data in real time, updating its position measurements every millisecond. But to be fully immersive, our tracking system also had to eliminate even minute delays and discrepancies between your physical movements and equivalent motion within VR. To help sync up these movements, we use a kinematic prediction algorithm that's been developed and tested through thousands of real user trials and can effectively predict exactly where the user is going to move in the milliseconds ahead. Our industry-leading expertise in computer vision and innovative use of Visual-Inertial Slam and constellation tracking delivered a system able to track your position and environment in real time with sub-millimeter precision, creating an experience effectively free of lag, jitter, and other VR-related discomfort. We also tuned the entire algorithm pipeline to optimize Insight for power consumption, enabling up to 3 hours of wireless use on Oculus Quest's internal battery. Oculus Insight demonstrates that you can reduce power and compute overhead in an on-device real-time tracking system, while also dramatically boosting precision. It's the first of its kind in VR, and a glimpse of the increasingly untethered and immersive experiences still to come.
Okay. Okay, yeah, to ensure that the user is safe while we are playing VR, we also have to build a guardian system that basically ensures that we are not outside of the space that is free, that the playground space. So basically we do a 3D reconstruction and detect when we are close to an object and make sure that we don't hit that object, or at least we get a warning if that happens. This is yet another video, another view of the SLAM system as it works internally. So basically you put on your device, you localize against a previous map if it exists, otherwise it is built from scratch. And then, yeah, you do a SLAM. You detect features, you optimize them, and you track them, as you can see here. What are the challenges for AR and VR? So first of all, it is very important to have robustness. So there are hundreds of thousands of users that will use this device in environments that we have never seen before. So it's very important that our approaches are super robust and very well tested. We must guarantee that tracking works in environments like very dark or changing light conditions, like or shiny surfaces. As I said, yeah, it's important to have a lot of benchmarking and metrics to ensure that we cover all the possible situations, and that's very hard. Personal experience. So we need to be super accurate because we are kind of tricking our brain, telling our brain that what we are seeing in VR is the actual reality, and then you need to be super accurate so that jitter and other errors do not make the experience bad. So we need to be super accurate. Then also very efficient, because at the end games are the ones that are taking all the consumption, all the power consumption and all the runtime and memory. So we need to be very efficient in in all of these axes. Calibration is very important, not only the first calibration that we do to the device, but also online calibration, as I said before. It's important to estimate all the parameters online. Lifelong mapping. So something that we do is to save the maps that where the user is playing, and then we can load them when a new session starts, and we can localize against those maps and improve them over time. So we detect features that are dynamic and that we have to remove, and also features that are static and that should stay. Finally, at least for AR, not for VR, but for AR, we need to do instantaneous initialization. And this is what I'm going to talk about in the next slides. So now I'm going to talk about our work where I collaborated with some of my colleagues from my office, Michael Burri, Jesus Priales, Christian Foster, and Luke Oth. So we work on a visual odometry system that doesn't require to initialize. Why is instant initialization important for mobile AR? So many AR experiences are very short in nature, like a few seconds, because users rapidly browse through different AR effects. And therefore, one way to increase user satisfaction is to initialize AR effects from the very first frame. However, on word-locked AR effects, where we depend on a visual odometry or a visual-inertial odometry pipeline, we need initialization techniques that require the user to move the phone. This is very inconvenient because sometimes the user doesn't move the phone, and then you will wait forever for the AR effect to appear. So we needed to work on a solution that will be accurate and will be accurate from the very first frame. So this motivated our work on a visual odometry system that initializes instantaneously and independently of the user motion and also independently of the structure of the environment. Currently, at least in academia, there are at least two techniques to do vision-only SLAM initialization. Yeah, let me clarify that here we are addressing this problem only from the vision-only aspect. So in the academia, we have mainly two techniques. One that uses indirect methods. Indirect methods basically are features that are extracted using some detectors, like Harris detector or fast detector, where you basically extract features that are very discriminative in the image, like the nose of the duck that I said before, and you basically track those features and use them for SLAM. So using these features, there are methods like estimating the essential or fundamental matrix or a homography if the scene is planar, and you can do that if you have a parallax between the images. On the other hand, we have direct methods, which basically what they do is to initialize a random map that with the hope that it will eventually converge to the right solution. So direct methods initialize either a random map or a constant map or anything that you can think of, but it is normally wrong, and it is a bad map, and it has the hope that it will eventually converge. So both of these approaches have some issues for our use case. In direct methods, the main problem is that they don't initialize instantaneously, so that's already a red flag for us. But it has other issues. For example, the parameterization is not minimal. We actually estimate more parameters that we need. It also depends on structure, and you need to combine different approaches. Like, for example, if the scene is planar, you need to do an homography. Otherwise, you need to do the fundamental matrix computation. So it is quite complex in that sense. And also, there is a solution multiplicity. You need to deambiguate bad solutions to get a good solution. Sometimes the only way to deambiguate is to just run tracking to see if your solution is good, and otherwise initialize again. So most of these issues are not present in direct methods, but as I said, the map in direct methods is initialized very inaccurately, and that's really bad because the map directly influences the parameters that you are estimating, and it can actually diverge, and in that case, you need to reinitialize again. So these two approaches are not good for us. this is the problem we are facing. So if the user is rotating the phone, as you see on the left, then you can never initialize using the previous approaches that I mentioned. But it's motivated our work, which I will explain in the next slides. Our proposal is a visual odometry that doesn't initialize. The first step of our proposal is to run an indirect 2D tracker. So we extract features that we track frame to frame, obtaining 2D feature matches between the frames. So once we have the feature matches between 2 frames and we know the pose of the frame number 1, then we can estimate the pose of the frame number 2. And just for clarity, the first pose, it can be initialized to anything, like the identity. So to estimate the relative pose between the 2 frames, we can use a relative pose estimator to estimate the rotation R and the translation direction, or U in this case. And this relative pose R and U can be estimated without any dependence on the map or any dependence on the user motion. So we can calculate these 2 parameters very accurately. Finally, we need to also estimate S, which is basically the scale or the magnitude of the translation to get the full 6-dot pose. For the scale S, we do need to estimate, we do need a map, but in our case, the good thing of our approach is that the map, it only influences the quality of the estimation of S, right? Because R and U are independent on the map. So our approach is pretty robust to a bad initial map. So yeah, I think I already explained this, but yeah, so our proposal is a pose estimator that decouples 6-dot pose to estimate R, T, and U in 2 parts, where R and T are independent. Or I think I changed, sorry, the parameters here. But before I said, so R and T are the rotation and the translation direction, and these one are estimated using the relative pose estimator, and finally the scale is S, that is estimated using the feature correspondences. So basically, to estimate the scale S, what we do is to minimize reproduction error, same as we will do with any boundary adjustment solution, but we only need to estimate 1 parameter, right? And everything else is treated as constant. So why our approach works and direct methods doesn't work? So as I said before, direct methods initialize an inaccurate map, and this inaccurate map is used to estimate all 6-dot parameters of the camera. So all the error that you have in your map is also propagated to the parameters of the camera, and sometimes it can diverge. And in that case, the pose that you are estimating is not great, and it's going to diverge, and then the map is going to get worse, and then you diverge and you have to reset. In our approach, R and U are always correct. The relative pose is always correct, and we only need to estimate S, which is a bit more complicated because the map is not accurate during the first frame. But in any case, that's not a problem, at least for our use case, because when the user is rotating the phone and the translation is very small, then the parameter S is going to tend to 0, and the user is not going to perceive any error in S. Only as the baseline increases, depth becomes observable, and so does the translation magnitude, which becomes then quantifiable, and then we can estimate it. So we do so we propose an approach that goes from rotation only to rotation and translation direction only to full 6-dot pose as the user moves the device, but we estimate all the parameters like always. But yeah, as I said, S will not be accurate for the first frames, but it will become accurate as the user moves. And in any case, the user will not perceive the errors during the first frames, as I will demonstrate now in the video. So we have proposed a 6-dot pose estimator that we can actually compare against the gold standard solution, which is boundary adjustment. Boundary adjustment, as you know, yeah, it does optimize the points and the camera poses, minimizing reproduction error. So we have compared our approach against that when in 2 cases. One, when the depth of the points is known, and the other case when the depth of the points is not known, which is our use case when the user starts to move the device. And the good thing is that our error is way smaller than bundle adjustment when the depth is unknown. So here is bundle adjustment when depth is unknown, and this is the orientation error, which is close to 10-15 degrees, and in our case it's always below 2 degrees. Here in the right we can see also the orientation and translation error when and as you can see our approach. The translation error is around 2-3 degrees for our approach, and it's bounded, so it doesn't depend on the number of frames, while bundle adjustment, it linearly increases if depth is unknown. So this demonstrates that our approach is actually useful for this use case, and we cannot use bundle adjustment for this problem. Okay, so we have, as the contribution of this work, we have developed a visual odometry without initialization by proposing a pose estimator that decouples the series of pose to estimate in 2 parts, the 5 degrees of freedom relative pose and the translation magnitude. We have showed that our series of pose estimator outperforms bundle adjustment solutions when the depth is not observable. And also, as you can check in the paper, our 5 degrees of freedom relative pose estimator also outperforms state-of-the-art solutions for the relative pose problem when priors are available. So yeah, we have some comparison in the paper also. And finally, we have released a dataset for the comparison of different relative pose algorithms. As a last contribution, we have integrated our results in mobile devices. So it is used now in both Instagram and Facebook. And you can see here an example of our system working in real time in a Samsung 8, I think. So we initialize this AR effect multiple times and with different motion patterns to demonstrate the ability of our approach. As you can see, it initializes from first frame and with any kind of motion. Here we get closer to the virtual dog, and in the next time that we browse the dog, then we do rotations and we also work. So it's general to the type of motion and also to the scene. Yeah. In this second part of the video, we do a similar validation, but in this case we move around the table, so it's a larger sequence, and we have a blue square, which is a very simple AR effect. So the white line that you see there is the ground truth, and the red line is the estimated pose. And as you can observe, they align pretty well. So now I'm going to briefly talk about a few projects. I mean, there are many projects going on, but I'm going to talk only about a few. So I have worked in headset tracking and also in mobile tracking, and now I transitioned a few months ago and I'm working on keyboard tracking. So we want to enable productivity so that people can, in the future, work in VR and collaborate and have video calls. And for that, one of the things that you need is keyboard tracking. So we are working on a keyboard tracker that it also uses similar techniques as the ones I saw before to detect keyboards and track them in real time. In this case, tracking is not working super well actually because the scene is probably not very well illuminated. But yeah, it's an example of how it can work. At FRL, they are also working on very accurate lens reconstructions using depth sensors and SLAM. And as you can see in this video, I mean, for me, it's hard to tell if this is a video or if this is just, I don't know, like one person recording the room. And one of the novelties of this approach is that they can actually reconstruct mirrors, as you can see here in the left part. So there's also a team working on realistic avatars. So these two guys you see here in the center are the avatar realistic representations of the two persons that are wearing these glasses. And the basic idea is to use camera and depth sensors to reconstruct the persons so that you can actually talk in VR and have a 3D experience.
What can you face to us? Well, I've always hoped you would ask me that question. Yeah, rolling my tongue. Yeah, not a lot of people can do that.
A codec avatar is a digital representation of a person. And so we build these to look like us, move like us, sound like us. And the purpose of it is to be able to connect people across distances. Time with, and not be restricted only to those people who live close by. That's the promise of it. And this is research work that we've done right here in FRL Pittsburgh. I hope you enjoy the demo that you've seen, and we all look forward to what the future brings. Thank you. Well,
Okay, yeah, finally I wanted to say a few words about Zurich. It's a place that has a lot of opportunities for computer vision, for SLAM, both in academia and also in companies. There are actually quite a few big techs here. So it's a place that I can recommend for living and also for finding positions in the future. And if you are interested about careers, we do have Intercept full-time positions available. So yeah, you can either apply or ask me if you want. As I said before, the presentation, there is even remote work available. And I will be working remotely in a few months from Zaragoza, actually. So this is a very nice thing that we have it. Yeah. So thank you very much, everyone, for attending. And if anyone has any questions, let me know.
Thank you very much for the presentation. Very interesting. Yeah, as you say, any questions? You can raise your hands. Oh, okay. You can ask. One.
Okay. Hi. Thanks for the presentation. It was quite interesting. So I have a couple of questions. So, and they are kind of like related. But the first one is that you present an example where there was mirror and glass surface reconstruction, and the question is kind of like how do you see an approach like for example like a nerve that they can also recover not only the geometry but also the appearance? Do you think that it would be a good idea to combine like let's say like this approach with a SLAM system? Or
what approach did you mention?
Neural radiance fields. NERF. It's a paper from Google where so basically they use a network to encode the geometry and the appearance of the scene.
Yeah, I'm not familiar with this work, and I also not familiar with the work from FRL. I mean, I wanted to present results, but but I know that they do the mirror thing using QR codes somehow. But I cannot tell you the approach behind this approach. So yeah, it's not my area of expertise, to be honest. Yeah.
Okay. Thank you.
Any other questions? Well, I have Javier, if you want to proceed.
Yes, so thank you, Alejo, for the presentation. What I was wondering while I was hearing your talk is that if you consider photometric-based residuals, because everything seems to be based on features in your system, but maybe photometric could have some advantage in some dark areas or textureless areas. So is there any chance that if you consider it, why in your case it's not attractive or appropriate, this feature?
Yeah,
photometric?
Actually we do use photometric error to match features. So we extract them using standard detectors, but for matching we do use path matching. And we try to make it robust to illumination changes. So yeah.
Mm-hmm. So yeah, then I will follow up with the curiosities. So why patch based matching and not descriptor matching?
So this was one of the reasons is efficiency, and the second reason is because we tested it. I mean, this is a decision that was taken quite a long time ago, even before I joined, I think. But basically, it was tested, yeah, and results from our thousands of datasets showed that, yeah, they were actually better.
So better in accuracy, in cost, or even in both, or do you?
Yeah, in accuracy and also in cost.
Okay, interesting. And yeah, about the extractors, yeah, if you have this patch-based matching, couldn't you use just simply any high gradient point or anything? Did you test it that?
No, I mean that was tested, but yeah, we didn't get better results. So we got better results with the standard detectors. Yeah.
Nice. Okay. Very interesting. Yeah. Thank you.
Yeah. No problem.
Anna?
Yes. Hi. So thanks for the talk. It was really good. This is not my area of expertise. I'm more on the graphics side, but I still enjoyed it a lot. So I'm curious because you said that you need it to be robust, of course, because I mean, depending on each other's houses, they may have like different furniture, different walls, and so on. So I'm curious, what would happen? How robust it is? What would happen if I have my playing room with a wall totally covered in mirrors? Would it still be robust, or is this like a particularly challenging case if I have like my full, like an entire wall full of mirrors?
Actually, what happens with mirrors is that they replicate what is behind, and you can kind of duplicate the room, and you construct like a virtual room in the other side. So you can, I mean, it depends. If the entire room like is full of mirrors, it's of course not going to work. Mm-hmm. But if you only have one wall of mirror, then you can actually, unless there are big distortions in the mirrors, you can actually use the features from behind, mm-hmm. as if the room was duplicated.
Okay, so maybe the issue would be just the guarding system, right? That it would believe that there's another room, but there's actually a mirror. I guess this can be easily solved, like with the current like HTC Vive and all systems. You would just like set the room with the controller, and then that's it. You prevent from hitting the walls. Yeah,
actually, the Guardian is not automatic, so mm-hmm. So you have to still be able to.
Okay, I see. Yeah, makes sense. Thank you.
The Guardian that I explained before, what is automatic is that it can also do intrusion detection. Mm-hmm. So if there are new objects appearing, then we can detect them. But, mm-hmm. But yeah, the case you said before,
I see. Yeah. Thank you.
Thank you.
Hi Alejo, it's Mingo.
Hello.
I think I heard in one of the videos that you got sub-millimeter accuracy, and I find it difficult to believe. Can you explain in which circumstances are you able to do sub-millimeter accuracy, and where comes this extremely high accuracy come from?
To be honest, I don't know where this sentence is coming from. It's from a video I didn't do. But I mean, sub-millimeter accuracy can be achieved if you are in a small room and it is, I don't know, very well textured. I'm pretty sure that if you go to a street or whatever, you're not going to achieve that. So if you are in a very restrained environment, small, then you can achieve that, but it's not a normal case. It's probably the best you can get in ideal conditions. Yeah, I agree.
Okay.
Yeah.
Thanks.
Juan?
I have a question. Maybe it's dumb, but I will try. So you mentioned in this from your method, like you mentioned this idea of like a decoupling. Could you explain that again? I was not sure what was the. So I guess that the advantage is in the optimization part, or why is better?
So yeah, I can explain it again. So basically, the main problem that we have is that during the first frames we cannot estimate the points. We cannot estimate depth. But using feature matches, so 2D matches, you can actually estimate the rotation and the direction of the translation. Okay, so you can do that using a relative pose solver. That's well known, and that rotation and that translation direction will be accurate. So we decouple these two parameters from the third parameter, which is the magnitude of the translation, and the magnitude of the translation is what we estimate once we have some points that are triangulated. If the points are not triangulated, then we assume they have constant depth, and then use that assumption to estimate the scale. Using constant depth is not great, I agree, but the thing is that during the first frames, it doesn't matter what scale you estimate because the scale is going to be close to 0. And that's why our approach works, because during the first frames, the user is not going to perceive the small scale, right? So once the user moves the phone, then you can start to triangulate features, and then the scale will become observable and accurate. So we decouple scale from rotation and translation direction. That's the point.
Okay, thanks.
Anna?
Yes, so I have a question from the YouTube stream. I believe it may be already partially solved with the answer you gave now to Juan Raúl. So the question is the following. Given that the scale is not accurate at the first moments, how is it possible that the virtual effect, so the dog in the example you showed, stays at roughly constant depth? I guess that's the assumption you make, this constant depth, right?
Yeah, so basically the scale is not metric scale, right? So it is so the initial scale of the dog you can decide. You can make the dog big or small, whatever you want. What we try is to make it consistent. So we make it consistent from the very first frame, and basically depth is assumed is constant for all the pixels to all the features, and that is giving you the initial scale of the object basically. So whatever you choose, like I don't know, like 1 meter, 1 centimeter, for the constant depth, that is giving you the initial scale of the dog, and that is preserved later on. Once the optimization converges for the
Thank you.
Okay, Jose Mari.
Hi, Alejo. Nice talk.
Hello. Hey, Jose Mari.
Well, regarding because I understood that the basic matching you do between frame is photometric matching with patches. You said that you synthesize the patches to compensate the different effects in camera motion. Do you explicitly estimate the normals of these patches in order to compensate better, or just has a patch without?
Yeah, for patch matching we do warping, so we take the normal of the patches into account to do the warping better, and we also make it illumination invariant.
And can you comment about how relevant is having this normal in this computation? Because it seems it's not easy to compute this normal, but if you had it, clearly it can provide you.
So we basically cluster points, and then in efficient way using a grid in 3D, and then we get the points that are close to the current point to estimate the normal. I mean, in most cases, in many cases, it's not going to be super accurate, but in drastic cases, so this works in. This especially helps in drastic cases, like I don't know, like there are big rotations between camera frames, and then in that case it helps. Maybe from frame to frame, is not a big help, but in extreme cases, it can help.
Okay. And this matching based on patches, I guess it can produce subpixel matches. Can you comment about how subpixel actually you think these matches are? If you really notice using these methods that the accuracy that you can get boosts.
Do you mean in the case of refinement for the?
Yes. Or if you think a comparison with point matches based just on descriptors, how useful do you find this patch-based matching in the system?
Yeah, actually, I haven't done that comparison. I don't have results. So I know we gained something, but yeah, I cannot tell you. I really don't know.
Okay. And something I don't know if I understood well. When you mentioned the back of words, you said something like you were learning on the fly this back of words. Is something I understood well, or you have a pre-compute dictionary, or is a dictionary that you are adapting for this room?
So I believe the localization works online. They are building a vocabulary online, and that's why it's called learning.
Can you comment about how beneficial is to have, let's say, a vocabulary for this room instead of a vocabulary for any room? Do you have any comment about how this can improve the performance?
So you mean like having a general vocabulary for all the rooms?
As opposed to building online a vocabulary for this room. It's like you have a bag of words which is specific for this map instead of a generic one, if this is the case.
Yeah. Again, sorry, I don't have some of your questions, but this will be something for the localization team. I have no work on this problem, to be honest.
Okay. And one last question regarding the scale that you say in the initialization. Are you estimating the absolute scale of the motion, or when you are saying scale, what scale are you referring you to?
So more than a scale, probably scale is not the best name. Is the magnitude of the translation. So we always estimate the magnitude of the translation with respect to the keyframe. So we do keyframe to frame, relative pose estimation, and then we need to estimate the magnitude of the translation. That's what we estimate.
But then you actually know how many centimeters the camera has translated.
It's up to scale. Yeah, it's monocular. This is monocular.
Yeah. Okay.
Yeah.
Okay. Thank you. Very nice work and very well explained as well.
Thank you, Jose.
Javier.
Yes, one last question. This slide that is already on, I'm looking at it. And my feeling is that you decouple rotation and translation from triangulation and scale. But actually, when there is a small translation, the direction of the translation will also be super noisy, I suppose. So why not decoupling entirely and say, okay, only rotation and then all the rest when I have enough translation, and then the direction, the scale, and the depth, the three of them will be nice.
That's just because, just to make it consistent, just because otherwise you have to introduce thresholds, like a threshold for when the translation is enough or when it's not, and that depends a lot on the scene. So this is very coupled everything. So you run the same algorithm all the time, and as you said, the translation will be super noisy, but that's not a problem because the magnitude of the translation will be zero in those cases. So you don't perceive it, and I think that's a nice property because you can use this approach for any situation. It doesn't matter if the translation is small or not.
Okay. But then you still need thresholds, right, to decide on the scale, for example, when you have enough motion to get the scale? Or?
Yeah, actually the threshold that you need is to when you initialize a point. That's the only one. So So basically, when there is more than 1 degree in the triangulation, then we consider the point is accurate enough, and then we start to use the new depth of the point instead of assuming that the depth is constant.
Okay. And for the scale is the same. When you have points with more than 1 degree, you get the scale. You start estimating it, or
No, sorry. So the scale is the same as translation magnitude, and this is always estimated. The only difference is that for the initial frames, this magnitude is going to be close to 0. So the translation will be inaccurate, but the parameter S here will be very close to 0 during the initial frames. Therefore, the U multiplied by S will be close to 0, and you will only see rotation.
Okay, so I think I understand it now. Yeah, so the S is always estimated to, but it is very close to 0, and then for triangulation is where you put this threshold of 1 degree.
Yes, correct.
Okay, nice. Okay, thank you. Understood.
Yeah, thank you.
Juanjo?
Yeah, thank you for your talk. Really interesting. I was wondering, in one point of your talk, you said that you store, let's say, the same map for the same room, and you are able to reuse that. And thanks to that, you are able to detect, for example, if something has moved in that map, and you can reject on, so you don't use that, let's say, outlier information. But my point is here is, imagine that you're playing with the Oculus. You have, let's say, a pet, for example, a dog, that are moving, or maybe other people moving around you. Are you able to use or to handle these dynamic objects inside your tracking pipeline? Let's say for estimating its trajectory, or making some warning for the player or something like that.
Yeah, for that we have a module called intruder detection or something like that. And basically what we do there, I mean, we don't use the features that we use for tracking. We just build a denser map and using the stereo cameras, and then we can understand that an object is invading the playground area, and then we inform the user that something is there, like an intruder, like a dog or a person.
And for that dense map, you're still using let's say a point cloud representation, or you using other kind of map representation, like for example voxels and all those stuff?
So we do a dense construction, but then we use voxels for representing the 3D world.
Okay, nice. Thank you very much.
Anna?
Yes, so I have another question from the YouTube stream. So the question is, Javi reads in the article that in order to do the optimization, the Jacobians are minimized. And what is the intuition behind minimizing this and not a measure of error?
So the Jacobians is a trick that you use because the error or the error that we are minimizing, the residual is the size of the residual is 1. So it was a trick that was proposed to do nonlinear optimization, where you need a prior of the pose that you are estimating, and for this kind of optimizations you need to minimize as many errors as parameters you're optimizing. So since we are optimizing 5 parameters, we need at least 5 errors to minimize. So that's why instead of minimizing the error, we minimize the Jacobians of the error to have 5 errors to minimize. The problem of this solution, which was proposed a few years ago, is that you are not minimizing the error, you are minimizing the Jacobians itself. So it's not going to be globally, the convergence is not going to be great in many cases. So what I propose in the paper is to combine both, the error and the Jacobians of the error and to get a residual of size 6. And in this case, we can increase convergence properties of the problem and we get better results.
Okay. Yeah. Thanks.
Thank you.
Okay. I think if there's no other questions, we can finish. Any other questions? Okay. Well, thank you very much, Alejo, for the presentation. It was very interesting. And well,
Yeah.
I hope to see you in Zaragoza when you come.
Yeah, we will see each other soon.
Thank you very much.
Yeah, thank you very much for the invite.
Thank you, Alejo.
Bye.
Thank you.
Muchas gracias, Alejo.